get that going. But I don't know if we already talked about conservation of angular momentum. I guess we can talk about it real quick. We've already talked about conservation of just momentum, right? When do you have a conservation of momentum? When is momentum conserved?
No other forces are in play.
When the net external forces are zero, right? When the net external forces are zero, then your momentum is zero. And roughly the way that you could get intuition for that is, we already showed that the derivative of momentum with respect to time is a force, right?
Yeah.
Because this is m times velocity. When you take the derivative of velocity, you get acceleration.
Mm-hmm.
And we also showed last time that the derivative of angular momentum with respect to time was equal to a torque vector, right?
Yeah.
Briefly remember that?
Briefly.
We had to use the product rule on a cross product. Do we need to redo it real quick?
The cross product?
Nope.
The derivative of this?
The derivative.
Do you think you could calculate the derivative of that? Do you remember what angular momentum is? What's angular momentum?
Angular momentum is
Momentum.
Your momentum vector? Well, not that one first. Maybe go back to torque and this will inspire you. What's torque?
it's the tangent force times the radius. Or the
What on earth?
right?
Got blood coming out of me. Not sure. Must have rubbed like a scab or something on the side of my head. There. And of course there's nothing in here. I don't know. I'll worry about it in a second.
It's only blood coming out of your head.
Yeah. Just need to go in here. Use a little bit of cardboard. Just not dripping down my shirt. Alright, I'll worry about that in a sec. Anyways. So going back to think about torque, how did we calculate torque?
It was position vector times
Your
the
position vector
force vector.
crossed with your force vector, right?
Cross, yeah.
Okay, so now what's your angular momentum vector?
Your position vector,
Times.
no, times your momentum vector.
Cross with your momentum vector. Remember, this is the angular version of momentum, just like this is the angular version of force.
Yeah.
And always going from our linear versions to our angular versions requires some sort of product with r, right?
Yeah.
I guess not always. Sorry. Sometimes it was a product of r the other way. Like we say that tangential acceleration was r times alpha. So sometimes it goes the other way. But so usually back and forth going between these angular things to our linear versions of them is require somehow a product with r. So if you just keep that in mind, you can usually guess at it. Right?
Yeah.
Okay. So the derivative now of this thing, what's the derivative of this thing? It's the derivative of the first multiplied by the second. So if we do the derivative of our angular momentum with respect to time, what's it going to be? It's going to be the derivative of this crossed with this. And I'm going to rewrite this one a little bit funny. Right?
Yeah.
The derivative of the first crossed with the second plus the first crossed with the derivative of the second. And what's the derivative of our momentum vector?
Just force, right?
Just force. It's just our force vector. And now a vector crossed with itself is
Zero.
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 So
That's
this
right.
is zero. And so you get the derivative of angular momentum is r cross f, which r cross f is our definition of torque.
Yeah.
So if the net external torque acting on a system is zero, then what?
How do you calculate? What's R? How do you calculate?
R, the position vector to where the force is being applied.
Position for where the force is being applied. What does that look like?
You're saying for when you're calculating torque, you're thinking about this R cross F?
Yeah.
Okay, let's go back to our door example. Here's the hinges, here's the door. And I apply a force right here, we'll say 10 newtons, and we'll assume it's perfectly perpendicular.
Okay.
And we'll say that the radius here is 3 meters. What's the torque then? It's going to be 30 newton meters.
Yeah.
So the r is the distance from the point.
It's the position vector from your axis of rotation
Axis of rotation.
to where the force is being applied. That's what r, that's the r vector. R by itself is just the magnitude of that vector. R by itself is just the magnitude of that vector. So the magnitude of r cross f is the magnitude of this vector times the magnitude of this vector times the sine of the angle between them. And I think I misled you guys last time about the sine of the angle between them with how I drew my picture. I don't think I lied to you, but I think with how I drew it, I made it a little bit misleading. So let me clear up the angle between them. Because if I have my position vector like this, in fact I might just like it, and I have my force vector like this, what's the angle between them? Is it this angle right here?
Yeah.
And the answer is no. To find the angle between them, you have to place them both at the same point. So you need to redraw your picture so that you have one vector here, and then another vector like that. So take that vector, stick it right there, that's the angle between them. That's the angle we were talking about.
That way it's actually sine.
And yeah, that way it's actually sine. So when I take the sine of this now, that's going to give me the component that way, and there we go.
Oh, I see.
So yeah, lied to you a little bit on that one.
Okay.
So glad we went on this random tangent and triggered my memory. Okay. Not sure why, but angular momentum. Okay. So the change in angular momentum with respect to time is given by your torque, right?
Okay.
So what happens if the net external torque on a system is 0?
Then I would assume you wouldn't have momentum.
Then your angular momentum isn't changing.
So it's
The
constant.
change in your angular momentum is given by torque. Torque doesn't mean you have angular momentum. Torque changes angular momentum. If I have a system that is rotating, so it has some angular momentum, it takes torque to stop it. If I have a system that's not rotating, it takes torque to start it rotating.
That makes sense.
Angular momentum is basically the momentum you have from spinning, from rotating.
Okay.
Right? You have momentum from your linear speed, which is what we just call momentum, and then you have momentum from the fact that you're spinning, which is what we call angular momentum. It requires a force to change your linear momentum. If you're out in space and you're going this way 1 meter per second, you're going to do that always and forever unless a force acts on you. Your momentum stays constant unless a net force acts on you.
Okay.
Similarly, if I take you in space and I start you spinning, you're going to be spinning forever until a net force acts on you to change that. So if there's no torque, there's no change in your linear momentum. The same way that if there was no force, there was no change in your momentum. If there's no force, your momentum's not changing. If your momentum's not changing, it's constant. Or in other words, it's conserved from second to second. Whatever your momentum is whatever your momentum is.
Okay.
That's what we meant by conservation of momentum. If I've got some system, and there's no external forces acting on that system, then whatever the momentum of that system is what the momentum of that system is. It requires a force to change the momentum.
Yeah.
Similarly, if I have a system with some spin, with some angular momentum, that system has whatever angular momentum it has, and that angular momentum is conserved unless some net torque acts on the system. Make sense?
Yeah.
That's what we mean by conservation of angular momentum. So we've talked a lot about a bunch of these things. Let's try and remember the last example problem we did and pick up from there. Did we do the example problem with a wheel with a box hanging on it?
Yeah.
Yeah.
We did that one? Let's see. Did we do a yo-yo?
Nope.
No? So that's one we're on? Alright, so let's do the yo-yo. And figure out what's going on here. You make a primitive yo-yo wrapping a massless string around a solid cylinder with mass m and radius r. So we've got our yo-yo here. Starts out right here. You're holding the string, and then over time, the yo-yo goes down to this position down here. We know the mass of the yo-yo. We know the radius r of the yo-yo. We know the moment of inertia of the yo-yo. We were told that this is a solid cylinder. What's the moment of inertia of a solid cylinder?
Just 1/2 m squared.
1/2 m r squared.
Okay.
Let's see what else we're figuring out. You hold the free end of the string stationary and release the cylinder from rest. The string unwinds but does not slip or stretch as the cylinder descends and rotates. Using energy considerations, find the speed of the center of mass of the cylinder after it has descended a distance h. So it'll follow some distance h. So we know what h is. We're looking for the velocity of the center of mass. Right?
Okay.
Okay. So first off, this is an energy problem.
So you want to use energy or formula?
So we ought to use our base, our always and forever formula. What's our always and forever formula?
Potential energy at the start.
The initial potential energy plus the initial kinetic energy plus the work you do on the system is equal to the final potential energy plus the final kinetic energy.
How do you know to you that it's an energy problem?
It's sad, but also the majority of the time that you've got something moving a definite height down. I mean, anytime I see an object falling, my first thought is, okay, it lost potential energy. And you know the yo-yo is going to be spinning, and they ask you to find the velocity. Those are both things associated with the energy.
And you can make the potential energy at the end 0 even though it hasn't hit the ground.
Yeah, you can call anywhere you want potential energy 0. I could call the top potential energy 0, and then this would just be negative.
Okay.
All that matters in the algebra is the difference between these two, which is always going to be the same. I can call this 10 and this 0. I can call this 1010 and this 1000. I can call this negative 100 and this negative 110, and maintain that the difference in their potential energies is 10, if it's actually 10. Doesn't matter which. Okay, so we got our base energy formula up there. So now let's start writing out what we know about the energies.
Okay.
What's the potential energy in the beginning?
MGH.
MGH. What's the kinetic energy in the beginning?
There is an
0, is that right?
0. What's the work going into the system?
0.
0. So this is equal to, what's the final potential energy?
0.
Yeah, we're choosing that to be 0. So then we just have the final kinetic energy.
Which is just 1/2
And notice that we have a rigid body moving in a linear motion while rotating, right?
Okay.
And what did we prove last time? We proved that the kinetic energy of the system now is going to be, we have 1/2 m, the velocity of the center of mass squared, plus 1/2 moment of inertia times omega squared.
Yeah.
How does that work? Oh, I'm on it.
These are both accounting for just the yo-yo.
Because it's also spinning.
Yep, this is the energy in its spin, this is the energy in its actual movement down.
Do we know what omega is?
No, we do not know what omega is, I don't think.
So we're gonna have to find what another equation to plug in for omega?
You make a primitive yo-yo by wrapping a massless string around a solid cylinder with mass m and radius r. You hold the free end of the string stationary and release the cylinder from rest. The string unwinds but does not slip or stretch as the cylinder descends and rotates. Using energy considerations, find the speed, VCM, of the center of mass, blah, blah, blah. Well, we know that the velocity of the center of mass, this point right here, it's always going to be the same height as a string that unwound, right? If
Yeah.
I would have drawn that right. So we actually know that the velocity of the center of mass is also going to be equal to omega times r. the center of mass is going to move down the exact same amount that this string unwinds. Omega times r is how much the string unwinds, or how fast the string is unwinding. This is how fast the center of mass is moving down. Those are the same quantity.
So we just plug in velocity of center of mass for omega?
So we can plug in omega as velocity of center of mass divided by r if we want.
So you only have to do
Right?
this.
Oh, because we're looking for velocity of center of mass.
Yes. So we can make this substitution if we want. And you'll see that r's cancel out over here. Plugging in the moment of inertia is what's going to make this look clear to you. So 1/2 m velocity of the center of mass squared, plus we have 1/2, and then moment of inertia was 1/2 m r squared, right?
Mm-hmm.
And then if we make our substitution of omega for velocity of center of mass over r, this is the velocity of the center of mass squared over r squared. And you see the r's cancel out, right?
Mm-hmm.
And let's go ahead and cancel out masses. So mass, mass, and mass all go out. R squared crosses out with r squared. And let's just write that really quick. So we have GH is equal to 1/2 the velocity of the center of mass squared plus 1/4 the velocity of the center of mass squared. Right?
Okay.
So add these two together, that's going to be 3/4, maybe one step at a time. Okay. So 3/4 the velocity of the center of mass squared, right?
Mm-hmm.
So the velocity of the center of mass then is going to be equal to 4/3 this thing,
Square rooted.
square rooted, exactly. Velocity of center of mass, 4/3 GH all under the radical. Okay, that's what we got. Okay. Next one. Racing rolling bodies. Oh, this is a cool idea. Just talk about it for a second to try and help you get an idea of it. Need another cylinder in the room. Solid cylinder. Okay. Here's the idea. We'll try and just draw it out, and then I'll just explain my picture since it's going to be super two-dimensional. We've got a ramp here, and on the ramp, one of the objects I place on the ramp is a big wooden log, perfectly cylinder solid log, all right? Which is nice and big, some big radius, big R, who knows. And then I also put this little marker right next to it, which we'll assume is also a completely solid cylinder. Maybe we cut it off, maybe we get rid of the ink with plastic, just make sure it's completely solid, but made out of completely different materials. And we have them set up so that they're both at the exact same height up the ramp, so that their furthest point is at the same height. And I release them
How
and
can
have
they
them
be at
roll.
the same height?
Huh? The same far up the ramp. That furthest point and that furthest point are the same far forward.
I see.
And I'm going to let them both roll down the ramp.
Okay.
You with me? Which one makes it to the bottom first?
The bigger one.
Is it frictionless?
Yeah, we'll say, well, no, it's not frictionless because you need friction to roll. So we'll say it's rolling without slipping. So this is a super ideal. This is something you could easily test if we just had another big cylinder. You can see it. And we could just perform this experiment ourselves. I mean, I guess I could combine two markers together and have it race one marker.
Okay.
But we'll use a big giant log and a little marker, and they both roll down. Which one do you think gets down faster? He says he thinks the log. What about you? Think little outruns big, or big outruns little, or do you think it's the exact same even though they're different materials and sizes?
I think they should be the same.
You think they should be the same?
If not the little one.
If not, then the little one. So you're just saying Peter's wrong. And it turns out when you roll these down, they're going to get there at the same time.
Okay.
Okay? So let's try one a little bit different. Let's say now I've got two with the exact same mass. Well, not the same mass, but we'll say two, the same materials. Same materials. And in one case, I have a solid cylinder. So we're only seeing the side of the cylinder, like a can of soup full of solid metal. So it's metal all the way through, right? And then we have another one that's so this one's solid. And then next to that on the ramp, we have one that's completely hollowed out. So it's more like just a pipe. So a metal pipe made out of the same metal as some completely solid metal sphere. And you roll both those down the ramp. Which one do you think is going to get down first? Or do you think they're going to be the same?
Well, I mean, I know it's probably the same, but it makes sense for the heavier one to get down first.
You say this one?
If you're ignoring like air resistance.
Ignoring air resistance, all that stuff, sure.
Well, then it's just gravity pulling it down.
Yeah, it should be the same.
So both of them the same?
Sure.
Sure? If they weren't both the same, what's your second guess?
Heavy.
This one?
Yeah.
Okay, the answer is this one will be second. So this one will be first.
What?
The heavier one will be first, in this case. And it doesn't have anything to do with the fact that it's heavier.
Why?
Because even if I make like these weigh the exact same, but this one is hollowed out, and this one's solid, yet they weigh the exact same, this one will still be this one.
Why?
So it turns out how fast these things roll down this ramp is a consequence of their geometry. It is not a consequence of the materials they're made out of or how massive they are. It's just a consequence of their geometry. Any solid cylinder will roll down this thing at the same speed, no matter what it is. Any hollowed out cylinder will roll down this thing at the same speed, no matter what it is. And any hollow cylinder will roll down slower than a solid cylinder.
Why?
We'll derive that. You want the intuition for it?
Yeah.
Its moment of inertia per unit of mass is higher up here than it is up here. So the more mass you have, the more gravity pulls on you, right?
Mm-hmm.
Yeah.
So this thing's moment of inertia per mass, what's the moment of inertia of an object like this? Do you remember what it is? Neither do I.
I think it's like 1/3 or something.
No, it's higher.
Oh, it is?
Because all the mass is further away from your axis of rotation.
Oh, I guess that makes sense.
Where's that table? Was it not in section 9? I thought
It was.
It was. So, yeah, for this one, it's just I is equal to
MR squared.
mr squared, and this one is I is equal to 1/2 mr squared. So you have to convert potential energy into kinetic energy as this thing rolls down, for both of them, right?
Yeah.
Since this one has a higher moment of inertia,
It has less velocity.
then it has its kinetic energy in rotation is higher, so its kinetic energy linearly is lower. This one's kinetic energy in rotation is smaller, therefore its kinetic energy in movement is higher. Because you're just converting potential energy to kinetic energy as these roll down. Does that make sense?
That makes sense.
So that was just a lot of talk. Now I assume that the exercise that we're doing is going to do some sort of proving some of this stuff. So let's actually go through the exercise problem now. Where were we? No. We did the yo-yo. Oh, we're right here. Okay. In a physics demonstration, an instructor races various bodies that roll without slipping from rest down an inclined plane. What shape should a body have to reach the bottom of the incline first? And so he's going to roll some balls, some solid cylinders, some hollow cylinders. What shape do you think reaches the bottom first?
Out of those two shapes?
So you've got a sphere, you got a hollow cylinder. Is that right?
Your sphere is wrong, your cylinder is right.
Oh, I missed my key.
Sure.
Sphere, and then we have the solid cylinder.
Is your sphere solid or hollow out?
We can do both for here. We'll say we have a hollow sphere and a solid sphere. So I think those are the four we're looking at. And of those four, which do you think reaches the bottom first?
Well, just the one with the lowest fraction in front.
But guess. Guess which
Solid
one you think reaches
sphere.
it.
Solid sphere.
The solid sphere, you think takes the longest?
No,
No.
reaches it.
Oh, reaches it first. Okay, and your intuition is correct. Let's really quick write up these values for these because I think we're going to need to use them in the problem. So, let's see. Erase that. Solid cylinder, we know that this one's 1/2. We just need the coefficient. So the coefficient for this one's 1/2 for a solid sphere.
Mm-hmm.
For a solid cylinder. For a hollow cylinder, it's 1. For a hollow sphere, it's 2/3.
And solid is 2/5.
And a solid is 2/5. Good memory. Okay, so those are our values that we're using, I guess. And now, what we're interested in is basically finding the velocity of the center of mass as these things roll down a ramp of some height. And I'll try and figure out what we're given. But I think you pretty much understand the problem. Place those things on some ramp. Shouldn't really matter what the incline is. And we place them all right there, let them roll down. And I think we know how high they roll down the ramp. An inclined plane. Let's just see if they use h in their equations. I assume they do. Yeah, they do. Okay, we should be fine. Okay, so rolls down some distance h. Right? So once again, for whatever this object is, let's set up our energy consideration. Once again, we have mgh, no kinetic energy and no work initially, is equal to no potential energy when it reaches the bottom, but it's going to have kinetic energy. So it's going to have 1/2 m velocity of the center of mass squared, right? Plus 1/2 I moment of inertia. So I'll use the letter K as just a constant for each of these. So that's going to change from each of those materials, but times K times omega squared
bar.
R squared, thank you. R squared, and then times omega squared. Right? Did my substitution right?
Where's your
This right here is moment of inertia.
Where's your mass?
Thank you. Because I have the K there, I didn't think about the mass. K times M times R squared times omega squared.
There we go.
Moment of inertia with some coefficient. Right?
Yeah.
So here's your moment of inertia for each of the objects, omega squared. Okay, there we go. Now, once again, since it's rolling without slipping, we know that the velocity of the center of mass is equal to omega times r. However much this object rolls is exactly how much it moves down this thing.
Yep.
Right? A case where this isn't the case is like when a tire peels out. When a tire peels out, this is no longer the case. So this is the case when your rotating object doesn't slip. Okay, so anyways, we can cancel out n's across this thing, so we get GH is equal to, we have 1/2 VCM squared plus K halves. R squared times omega squared is just going to be VCM squared, right?
Yep.
Multiply through by 2 and factor out the VCMs. So I'm going to get 2GH is equal to, we'll have 1 plus K times VCM squared. Good with what I did there?
Mm-hmm.
Multiplying that by 2 is that. Multiplying this by 2 gets rid of the half. Multiplying this by 2 gets rid of the half. And then factor that out. We have VCM1 and then K VCM squared. Good?
Yeah.
Alright, and so the velocity of the center of mass squared is equal to, or not squared, square root, is equal to the square root of this divided by this. 2GH divided by 1 plus K. So if I want to make this number bigger, what do I want to do to the denominator? Do I want this denominator bigger or smaller?
Smaller.
I want the denominator smaller.
Why is that?
What number is bigger?
One to the left.
Because it has a smaller denominator.
Oh, I see.
Smaller denominator means bigger number. So, for the velocity of the center of mass to be bigger, we need the denominator to be smaller, which means we want k to be smaller, which means whichever one has the smallest k, namely the solid sphere, will be the one that produces the biggest velocity of center of mass. Right?
Yeah, that makes sense.
Furthermore, the slowest one is going to be the one with the biggest k. Pretty cool, right?
Yeah. Do we do example problems that actually use like numbers for like the height and
I don't know. I can only tell you what the next example problem is.
Okay.
How to do these ahead of time. For the primitive yo-yo in example 10.4, so going back to the yo-yo that we did. Oh, we still have it on here. How lucky. So coming back and looking over here at our yo-yo. For the primitive yo-yo in example 4, find the downward acceleration of the cylinder and the tension in the string. The downward acceleration, so we're looking for, at the bottom, we want the acceleration of the center of mass. That's what we mean by the downward acceleration.
Okay.
And what else? And the tension in the string. So when it rolls down here, once it gets down here, kind of made that thick now, so it's going to be hard to put an arrow on. So once the yo-yo rolls down here, then there's going to be some tension in the string T holding it up. Right?
Okay.
Mm-hmm.
Okay, so notice now, how's the best way to do this? What did we already have here? We know our moment of inertia already. Here's what I'm thinking. The T here, the tension here, is the only torque on the system giving it its angular spin. So all its kinetic energy, or all its rotational energy is coming from this torque being there. Let's see, is that the right way to think about this? Some of the torques, maybe we're overthinking it with the energies. Let's go back to just looking at the forces and the torques and see what we can think about. So the forces in the x direction is obviously going to be 0, so let's just not even think about that. This is a totally y-dimensional problem, right?
Okay.
The forces in the y direction, at this point, we're going to have, we know the mass of this thing, so we have, let's call this way the positive direction, since that's the way it's moving.
Okay.
So in the y direction, we have mg pulling this thing down, right?
And then minus your tension.
And then minus our tension pulling it up, and then that is going to equal the mass of this thing times its acceleration of its center of mass.
Yeah, how'd you get that?
Okay. This is the total force acting on it,
Mm-hmm. Oh,
and the net force is mass times acceleration.
Oh, I see.
yeah.
Yeah.
So its mass is m, and then how is it accelerating? However the center of mass is accelerating, right? Get with that?
Mm-hmm.
Now the torque in this is going to be equal to the tension times R, right?
Mm-hmm.
Tension times R times the sine of the angle between them, which is going to be 90 degrees, which is 1.
Yep.
Didn't we just say that torque is the only thing, or the tension's the only thing making the torque in the system?
Right, so what is, but calculate the torque in the system. The torque in the system is the tension pulling up at a distance R over.
Okay.
So here's our torque, right? But another way that we can write our torque is also equal to
Moment of inertia times alpha.
moment of inertia times alpha. The other way of thinking about mass times acceleration, right?
Okay.
Now, since this thing is rotating without slipping, we also know that alpha is equal to r, we also know that our acceleration of our center of mass is equal to alpha times r, right?
Yeah.
Or in other words, well, we can leave it at that for a second. So, I'm going to drop the t out of this. You okay with that? The torque there. So we know tension times r is equal to I times alpha. And so we're going to have two equations with two unknowns, our two unknowns being tension and acceleration of the center mass.
Okay.
So let me rewrite this one really quick. So rewriting that one, we have TR is equal to 1/2 m r times acceleration of the center mass.
Yeah.
Because we took the other r and combined it with that to get that. Good?
Yeah.
So now we can, well, I'll just leave that there. Why not? Okay, so now it doesn't really matter which way we do this. We need to pick one equation, solve for a term, and plug it into the other equation.
You can just divide by r.
Oh, thank you. So, yeah, take this one step further. T is equal to 1/2 m times acceleration of center mass. Dividing both sides by r, right?
Mm-hmm.
And so, since we already have the solve for t, may as well just stick that up here and solve for ACM, right?
Okay.
So I'm going to take this and plug it in up here. So we get, and we'll come over here to give ourselves some room to write. Oh, this can start right here. We have mg minus 1/2 m times the acceleration of center of mass is equal to m times the acceleration of center mass. Oops. I wrote my m big. I wrote that weird. M times acceleration of center of mass. Right?
Mm-hmm.
And then obviously what can I do?
You just add.
Well, let's just cancel out
Divide by
masses.
m,
real quick.
yeah.
Yeah. So cancel out all the masses, and I'm going to move this to the other side. I'm going to plus 1/2 acceleration of center of mass to both sides.
So 3/2.
Perfect. So G is equal to 3/2 the acceleration of center of mass, or in other words, acceleration of the center of mass is equal to 2/3 G.
Interesting.
Which is a number.
Which is a number. But notice the amazing thing that the acceleration, once again, mass is completely canceled out of this thing. The only thing dictating how fast that fell was the geometry of this thing. Changing the moment of inertia is what's going to change that. So how heavy your yo-yo is doesn't matter. It's the shape of your yo-yo and how the mass is distributed that matters.
That makes sense.
So now we have the acceleration of center mass. We can come plug that in to get the tension. So now the tension. Now obviously tensions can't depend on mass, because if you had a really heavy yo-yo, that would snap your string.
Mm-hmm.
But if your string was like basically perfect, then it wouldn't matter, right?
The tension would still increase a lot. You're just saying, what's a perfect string? A string that can handle infinite tension?
Yeah.
The tension's still going up though.
Okay.
So I'm saying it makes perfect sense that mass shows up when calculating tension though. Because tension is like how hard that string's being pulled. Anyways, what's our tension now? So we're going to have 1/2 times 2/3 is going to give us 1/3. 1/3 the mass times the acceleration of center, times G. So it's only 1/3 the weight.
Yeah.
Okay.
Which is pretty intuitive. If it's accelerating downwards with 2/3 G, then we're only fighting 1/3 G and holding it up, so we need to hold up 1/3 its weight. Because we only need to cancel out 1/3 of the acceleration. Good? Well, we could probably double check. Acceleration of center mass, 2/3 G, tension, 1/3 mg. Okay. Acceleration of a rolling sphere. A ball rolls without slipping down a ramp, which is inclined, I don't know, that one's pretty similar. let's just keep going. Calculating power from torque. Okay, we didn't do an example with that. Calculating power from torque, we showed you what this was last time, but let's remind you of it. And remind you of its cousin. So our cousin from a couple weeks ago was one of the ways to calculate power was to use, what was it?
Energy per second.
Force times velocity, I think?
Yeah.
Force times velocity.
velocity.
The easy way to do it, power is the change in work with respect to time. That's a trivial way you can always compute it. So always and forever, here's power. These were just some tricks that are sometimes useful.
Okay.
Make sense? And so the other one that we found now is that power is also equal to the torque times omega. We're talking about in a rotating system. So that's the equation that we need to keep in mind here for this example, I think. So an electric motor exerts a constant 10 Newton meters torque on a grindstone, which has a moment of inertia. So, setting up our problem now, we know that we have torque is equal to 10. We have our moment of inertia for whatever this is equal to 2. About its shaft. So we're rotating some grindstone, I guess. So I'm not sure exactly what this is, but so we've got some grindstone here.
Mm-hmm.
And then there's like some shaft in the middle that coming out of it that it's rotating around, so it's rotating this way. With some speed, who knows, omega.
Yeah.
The way that we're creating this is there's some force being applied on it somehow, which is creating a torque of 10. So maybe the grindstone is just attached to the shaft and the shaft is spinning with some torque 10. And it has a moment of inertia of 2. Excuse me. And it's just rotating. Okay. Let's see, about shaft. Okay, so the system starts from rest. So initially the grindstone's not running, then we turn on the system. So we start applying a torque to it.
Okay.
And so just to help give us a sense really quick, we know one of the ways we can think about torque is moment of inertia times angular acceleration, right?
Yeah.
And so when we turn it on, we start an angular acceleration of 5 radians per second squared.
What are we looking for again?
I'm not sure yet.
Oh, okay.
Just trying to keep intuition for the problem. Oh, find the work done by the motor in 8 seconds. In 8 seconds, and the grindstone kinetic energy K at this time. So find the work done and the kinetic energy that we get. So going back to our work calculations, you remember that work in its most basic form was our force in the x direction times dx, or times some x, right? Some x displacement.
Yeah.
Yeah.
Maybe put like a delta x there, some displacement. Well, our work in a rotational form is going to be the torque we apply in whatever direction times the displacement of our angle.
Yeah, that makes sense.
So we know the torque, we need to know the displacement of angle that occurs over 8 seconds. Our time here is 8 seconds. I think. 8 seconds. Okay?
Displacement in time is 8 seconds?
No, our time is 8 seconds, so we need to figure out displacement.
Oh, okay.
So we know that our acceleration is a constant,
Yeah.
right? And so with that, we're able to figure out what our velocity is going to be, our angular velocity, and what our displacement is going to be. It's going back to the kinematic equations, right?
Yeah.
Oh, but the angular ones.
Yeah, but the angular ones. So I know that theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared.
Why do you want that one?
Huh?
Why do you want that one?
That's how we're going to calculate our theta displacement over 8 seconds. And we also know that omega is equal to omega naught plus alpha t. And that can help us get our omega, which I think we'll need for kinetic energy. But anyways, so we can use this equation to figure out how many radians does this thing spin, how many radians does it turn in 8 seconds? Okay. Well, we know that theta is equal to theta naught, we'll call its initial position 0.
Yeah.
What's its initial speed?
0.
0. So it's just equal to 1/2 alpha times t squared. Right?
Mm-hmm.
So 64 divided by 2 is 32. What's 32 times 5? Is that 160?
Yeah.
Yep.
So our displacement, theta, after 8 seconds of this thing running is 160 radians. You with me? So then our work is what? How much work did our motor do in 8 seconds?
Just 1,600.
1,600
Joules?
joules. Okay. Now, I forgot what we were looking for. Oh, we were looking for the work. So we found the work, and then there was a second part, I think.
Yeah, we're looking for.
And the kinetic energy. And then the average power. So then kinetic energy, then the average power. We can do average power in 10 seconds really quick. Let's just do the average power used. How much power was used per second?
200.
How did he get that?
Took it and divided it by 8.
Yeah, just take the work we got, divided by the time, and we get 200 what? Joules per second,
No, it's watts.
which is a watt. Good? So average power, that one's real simple. But now, what else do we need? Kinetic energy. Okay, we need to calculate the kinetic energy now. Now notice that, what's our universal equation? It's right here.
Mm-hmm.
Anytime we talk about energies, we can always come back to this universal equation.
Okay.
So let's fill it out. What's the initial potential energy?
0.
What's the initial kinetic energy?
Wait, the potential energy is.
0.
Oh, because it's just the work. That's right.
Initial potential energy, 0. Initial kinetic energy, 0. Work that goes into the system, 1600s. But yeah, we'll just put a W there and plug it in later. Is equal to, what's the potential energy in the end?
0.
0. What's the kinetic energy in the end?
1/2 mv squared.
No.
1/2 I omega squared. It's not moving linearly, it's just spinning. So all its rotational energy is in the fact that it's spinning.
Okay.
And I'm pretty sure that we know that this, oh, they gave us a moment of inertia. 2. So 1/2 cancels out with 2. So this is just equal to omega squared. Wait, what are we trying to figure out?
Omega.
Find the velocity. Angular
The
velocity.
kinetic energy.
Were we just looking for the kinetic energy? Find the work done by the motor in 8 seconds and the grindstone kinetic energy K at this time. Well, those are both the same. Okay, so we didn't need to find omega. Sorry. The kinetic energy after 8 seconds is 1,600 joules. Because all the work went into giving it kinetic energy.
Yeah, because it didn't have kinetic or potential energy.
Because our equation is work is equal to K2. So what's K2? It's the work. Okay. Yeah, overthinking there a little bit. So let's see. Our theta, 160 radians. Yep. The work, 1600. Yep. Kinetic energy, 1600. Yep. Average power, 200 watts. Yep. Okay, we did it. A lot easier than I thought. Okay, example problems with angular momentum and torque now. A turbine fan in a jet engine has a moment of inertia of 2.5 kilograms meters squared. So let's see. So turbine fan in a jet engine has a moment of inertia, I is equal to 2.5. So we've got I is equal to 2.5. about its axis of rotation. As the turbine starts up, the angular velocity is given by 40t squared. So our angular function for our angular velocity is 40t squared.
Okay.
Find the fan's angular momentum as a function of time and find its value at 3. So we're looking for angular momentum as a function of time. Right?
Yes.
Okay. How do we calculate angular momentum?
Just moment of inertia times omega.
Just moment of inertia times omega. So 100t squared.
Yeah.
Gives us our angular momentum at any time.
That's it?
Well, that was the first part.
Yeah.
Find the fan's angular momentum as a function of time. Find its value at t equal to 3 seconds. Wow, that's 900. Find the torque on the fan as a function of time and find its value at 3 seconds. Okay, how do we go from angular momentum to torque?
Integral.
Other way.
Derivative.
Derivative. You
Yeah.
take the derivative of momentum to get force, you take the derivative of angular momentum to get torque. So what's my torque as a function of time?
The derivative of
Which is, tell it to me,
200t.
200t. And what's my torque at time 3?
600.
600. Now we're missing our units on these, and I don't have what these units are memorized. So torque is kilogram meter squared per second squared. So this is kilogram meter squared per second squared. Oops, kilogram meter squared per second squared. And so, if I did that right, they put their units all over the place in this. Oh, per squared, just per second. Okay, and then torque, that one's easier. This is just Newton meters. And 600, 900, let's check those actual numbers. 600 on the torque, and 900 on the
Angular momentum.
angular momentum. Good. Okay, now our next one, remembering that angular momentum is conserved in solving this next problem. Very common problem, something you've seen 100 times. Maybe you've seen ice skaters spinning on ice, and when they try to spin really, really fast, what do?
They lose control.
Now, you'll notice that when they start to spin, they have their arms outstretched, and then they pull their arms in, causing them to spin really, really fast.
And then when you slow down, you just pull down.
Yeah, so cool thing to see. We don't really have a way to demo it, but if I could stand on something that was we could rotate on with 2 heavy weights in my arms, and if you guys started spinning me, once I was spinning, if I pulled those weights in, I'd start spinning faster and faster. And if I put the weights back out, I'd slow down.
And we're going to prove that?
We're going to do a problem where that's what's happening.
Okay.
I'm just getting that from the image. I haven't read it yet. So a physics professor stands at the center of a frictionless turntable with arms outstretched and a 5 kilogram dumbbell in each hand.
Physics professor.
Yes. So we've got our physics professor, and he's standing here, holding a dumbbell over here, and holding a dumbbell over here, and he's standing on a turntable which is spinning without any friction.
Okay.
Good? My picture's way better than yours. Trust me. Okay, so we know the mass of each of these is 5 kilograms. So the mass of that and the mass of that. He is set rotating about a vertical axis, making 1 revolution in 2 seconds. So initially, omega naught is 1 revolution in 2 seconds. So what is that in radians?
1 revolution in 2 seconds. That's just 2 pi radians. 4 pi.
If I'm going 2 pi in 2 seconds,
Oh, just pi radians.
then I'm going pi radians per second, right?
Okay.
So that's his initial speed. Find the final angular velocity if he pulls the dumbbells into his stomach. His moment of inertia without the dumbbells. So his moment of inertia when the professor's arms are just outstretched. So the initial moment of inertia of our professor is equal to 3. And his final moment of inertia of our professor is equal to 2.2. 2.2. The dumbbells are 1 meter from the axis initially and 0.2 meters at the end. So R initially is equal to 1, and then R in the end is equal to 0, or 0.2. Okay, so help you understand these numbers. 3 is a professor's moment of inertia when he has his arms outstretched, ignoring the dumbbells.
Okay.
2.2 is his moment of inertia when he's standing like this, ignoring the dumbbells.
22 or 2.2?
2.2. There's a decimal point there. Gets smaller. If I pull my arms in, my moment of inertia has to go down.
Okay.
If I'm spinning around this axis. Because this puts the mass further away, this brings the mass closer. Right? So then on top of that, he's also holding 5 kilogram dumbbells in each hand that he brings in as he does this. Those are also going to affect his moment of inertia. So the total moment of inertia in the beginning, the moment of inertia in the beginning is a professor's moment of inertia in the beginning, plus the moment of inertia from these 2 weights.
Yeah.
So we have 2 identical scenarios of the radius is 1 times the mass is 5. So 1 squared times 5, or we'll write the mass first. 5 times 1 squared, like that, right?
Okay.
This right here is the moment of inertia of the 2 weights. The moment of inertia of 1 weight is the mass times its radius squared. We have 2 of those because he has a weight in either hand. And then this is the moment of inertia of the professor ignoring the weights. Add those together, that's his total moment of inertia at the start of the system, right?
Okay.
Yeah.
And the moment of inertia at the end of the system is 2.2, the moment of inertia of a professor when his hands are like this. Plus, we have those 2 weights, they have mass 5, and they're now
0.2.
0.2 squared. Does that look weird? Here, I'll just do another parenthesis. 5 times 0.2 squared. That's the final moment of inertia, right?
Okay.
Now, no torque acts on the professor as he moves those weights in and out, right?
Mm-hmm.
There's no net torque acting on him. No one's running up and pushing him.
Yeah.
So angular momentum is conserved. So I know that I naught times omega naught is equal to I1 times omega 1, right?
Okay.
We know omega naught, we know I naught, we know I1, we're looking for omega 1. We're looking for his angular speed when he pulls in the weights.
That makes sense.
So his angular speed when he pulls in the weights is equal to I naught times omega naught over I1, right?
Yes.
And so we can quickly calculate those numbers. So we have 3 plus 2 times 5 for I naught times omega naught was pi. And we have divided by I1, which is 2.2 plus 2 times 5 times 0.2 times 0.2. Okay, and we get 15.7, which comes out to 15.7. I guess we could have left this as a ratio of just pi, because we could have just done this divided by this times pi. Maybe that's a better way to do it. So this is equal to I naught over I1 times omega naught, which is pi, right?
Yeah.
I naught is just 13.
Huh?
I naught is just 13.
I naught is 13, so we have 13 divided by 2.2 plus 2 times 5 times 0.2 times 0.2, which is equal to 5.
5 pi.
So it's equal to 5 pi. So his speed increases by a factor of 5. He's spinning 5 times faster than he was before, pulling in the weights. Huh?
That's a lot.
Yeah, it's a decent amount. Omega 2 is 5 omega 1s. Okay. Are they continuing the problem? We did everything it said, right?
I think so.
Evaluate the angular momentum. Oh, that's a cool point to point out. Really quick, think about the energy now in the system. So the professor was like that. He has some angular kinetic energy, right?
Yeah.
As he pulls the weights in, what do you expect to happen with the kinetic energy? Should it go up or down or stay the same?
Stay the same.
Should go up. The energy has to go somewhere, so keep that in mind.
Oh yeah, so if he's spinning faster, then it goes down.
But his moment of inertia goes down as his speed goes up.
Yes, but energy is still conserved.
Yeah, so I'm asking about the energy. We'll calculate the kinetic energy when his arms are out. We'll calculate the kinetic energy when his arms are close to his body. What do we expect between those two numbers?
For him to speed up.
We expect for him to speed up,
But they'll be the same.
but what about the kinetic energy? Kinetic energy has to do with both your moment of inertia and your speed, right?
Yeah?
Well, do I have more energy when I'm spinning like this? So I have some energy. If you put me on some turntable and you spin me, I have some kinetic energy in my spin, right?
Yeah.
If I pull my arms in, I'll spin faster since my moment of inertia went down. My angular speed goes up. But do I suddenly have more kinetic energy?
No.
But you're spinning faster.
But I'm spinning faster. But I have less moment of inertia. But do I have more kinetic energy?
It's the same.
It's the same?
Yeah.
Same kinetic energy?
Same kinetic energy.
Uh-oh. Let's see what happens.
How's that potential?
Yeah, it makes 0 sense, right? So let's calculate it. Let's calculate the kinetic energy in the beginning. I guess I used a 0 instead of a 1. Kinetic energy in the beginning is 1/2 I omega squared, right? And kinetic energy in the end is 1/2 the moment of inertia at the end times omega at the end squared.
Okay.
With me? This is equal to, what was this moment of inertia? 13. So we have 13 divided by 2 is 13/2 pi squared. Right?
Mm-hmm.
Yeah.
I know, right? And then on this one we have I1. That's a really small value. So, well, not really small, but 2.2 plus 2 times 5 times 0.2 times 0.2 is 2.6. So this is 2.6 divided by 2 is obviously 1.3. So this altogether is 1.3. So all right, that's 13 over 10, 1.3. Times omega 1 squared, so times 25 pi squared, right?
Mm-hmm.
Okay.
So 25 times 13, let's see, can we cancel anything out? Oh, we can cancel a 5 out top and bottom. Let's do that. You with me?
Mm-hmm.
So canceling out 5 top and bottom leaves 1 5. What's 5 times 13?
480.
What?
5 times. Oh, it's 65.
Okay, yeah, 5 5 times 13, 65. Another 5 canceled out down here, leaving a 2. Uh-oh. Kinetic energy went up a lot.
Where did it come from then?
Where did it come from? There's a question. I had to do work to pull those weights in.
What work did you do?
I had to fight centripetal acceleration.
Oh, that makes sense.
Right?
Yeah.
So there is something weird going on, and then when deformation is also going on, there's some deformation of the object. When I pull my arms in, I'm now deformed from what I was before. Before my form was this, afterwards it was this. Notice that when we've been applying these laws, I erased it, but we've always been talking about rigid bodies, bodies whose shape don't change.
Yeah.
Bodies whose shapes don't change are a lot easier to work with when we're talking about energies than bodies whose shapes are changing all over the place. It's kind of like an equation. When a collision occurs, energy is not conserved, necessarily. Energy is conserved, but it's not easy to track is what I mean to say. When two cars crash on a highway, and they have a perfect head-on collision, law of kinetic energy, those two cars crash, and now the cars aren't moving, where'd the energy go?
Into deforming it.
Into deforming the cars, which means going into like heating up the materials. A lot comes out as heat, sound, vibrating things. Deformation, yes.
Okay.
So the energy goes all over the place, and it's hard to track what happens with the energy, right?
Yeah.
And it's in situations like that where the energy is really hard to track that we fall back on using momentum, conservation of momentum. Because even when two cars crash, as gnarly as that is, tracking the resulting angular moment or the resulting momentum is real easy because momentum is conserved in that collision.
Yeah.
So energy can be tricky. Sometimes it's easy to lose track of how energy got into the system or where the energy went. Energy is always conserved, but a lot of times it's a lot trickier to talk about than just something like momentum. So oftentimes we use momentums to figure out our velocities rather than energies, rather than relying on kinetic energy. That's why conservation of momentum is such an amazing concept, both angular and linear. Because even in absurdly complex situations, it's so easy to calculate. Because two cars colliding into each other, that is absurdly complex. I can tell you the angular momentum I can tell you the momentum of the cars afterwards if I know the momentum of the cars before it. Because momentum is conserved. If you have a star that goes through supernova, I can tell you the momentum of the star after supernova. It's the same as it was before it goes through supernova. It's all conserved. Even though what's going on with the energy is completely gnarly, the momentum is still conserved. Okay. Let's see, that one's kind of just a collision one. Okay, we can do that real quick. We won't worry about the completely big pictures that they have there. But let's say I've got some circle thing here, some big circle thing, and it's rotating with some speed, omega A, and it has moment of inertia A. You with me?
Okay. Yeah.
And I've got some small circle thing, and it's rotating with omega B, and it's got moment of inertia B.
Mm-hmm.
Let's pretend that these things are like perfect magnets or something like that. So they're spinning, and somehow, without affecting their spinning, I shove these two things together. So they stick together now. What's the resulting spin? That's what we're calculating. You with me?
How do you find the resulting spin then?
Angular momentum is conserved. What's the angular momentum in the beginning? It was moment of inertia A times omega A plus moment of inertia B times omega B. And then when I stick those two things together, now their moment of inertia is going to be the sum of both their moments of inertia, right?
Yeah.
With some new speed, omega. Who knows what that new speed is, but now since they're combined, they're going to spin with the same omega. What's omega? Omega then is equal to, I'll just write it right here, omega is equal to this divided by this plus this, right? Ignore that side for a second now.
How do you know that?
Okay, sorry. Shouldn't have done that. That was terrible. You good with this equation?
Yeah.
Okay. Divide both sides by moment of inertia A plus moment of inertia B, and we get omega now is equal to moment of inertia A times omega A
yeah,
plus
got it.
moment of inertia B times omega B, all over moment of inertia of A plus moment of inertia of B. This was identical to when you had two things with momentum going along and they collide and stick together. You did this exact same thing, except for these were masses and these were velocities. Identical situation.
Okay.
Okay.
Wouldn't the angular momentum just go to 0? Because one of them's going this way and the other.
They're both rotating the same way. Sorry. I
know,
can't
but
draw the picture.
If you stuck a small one on the big one, and they were both turning like this one would slow this one down. Or this one would go the other way, like gears.
So out of these two things, I mean, it's possible they switch directions. That's possible. Just like with two velocities when they collide. It could be that they collide like this. One's just going faster than it and they stick together. Or it could be they're going like this and one of them changes directions. Or if they both have the same exact momentum, they just stop. So same thing could happen here. Just with spinning direction.
That makes sense.
So wouldn't the resulting one just be omega A minus omega B?
No, no.
Because it's spinning like this, and then the other one comes, and it's trying to slow that down.
It might slow it down some.
And then the other one, the B has to go the opposite way.
If this is slower than this, but they're both spinning the same way, the resulting spin is going to be slower.
And B is going to completely switch directions.
No, it's going to... They're spinning the same direction.
I know, but they would have to switch directions if they touched each other.
Let's redraw this. So here's something and it's spinning this way, right?
Okay.
And it's spinning that way with some speed. And now I've got my marker. Well, pretend that this was circular, and it's spinning at a slower speed. And let's pretend that this is a magnet and this is a magnet. And they're floating in space. When this sticks to this, it's going to slow it down some, but now it's going to spin with it.
Oh, you mean on top of each other?
Yes. Oh, sorry.
Because
Yep.
if you just took that one on the side of it.
Oh, you were thinking about shoving up against each other.
Yeah.
Yeah. Okay. Nope. Sticking on top of it. That's what I meant. Sorry. Yep. Good. That's the problem with not being able to draw. Huh?
You're limited to 2 dimensions.
Yep. Good. Okay. Next one. A door 1 meter wide with a mass of 15 kilograms can rotate freely about the vertical axis on its hinges. A bullet with a mass of 10 grams and a speed of 40 meters per second strikes the center of the door in a direction perpendicular to the plane. Find the door's angular speed. And then is kinetic energy conserved? So let's draw this. Here's my hinges. My door is hanging down like this. And bird's eye view of the door, looking down on it. Right?
Okay.
Okay.
The door is 1 meter. A bullet is being shot and hits right in the center of the door.
Okay.
So it comes like that, so the door is going to start swinging, right? It's going to swing open
Mm-hmm.
from the bullet hitting it. We're going to assume that the bullet completely embeds itself in the door. It doesn't go through the door.
Got you.
Okay? So we know the mass of the door. We know the mass of the door is 15 kilograms. We know the mass of the bullet is 10 grams. Right?
Okay.
And we know the velocity of the bullet is 400 meters per second. And I think that's all we know. 1, 15, 400, 10. Okay, those look like all the numbers. So now the question is probably something like, what's the speed the door swings open with or something like that? Find the door's angular speed, yeah. So we're looking for omega here. You with me?
Mm-hmm.
Once again, we're going to use the fact that angular momentum is conserved.
Okay.
So the very instant the bolt comes into contact with the door, let's think about that scenario. The very instant the bullet comes into contact with the door, then the bullet has moment of inertia what? What's the moment of inertia of the bullet?
It's a moment of inertia. Why would you want that? 'Cause it's not rotating.
It's from here on out, the instant it touches the door, the bullet now rotates. Because it's going to follow the door. So it's like the bullet from this point onwards is following a circular path.
Okay.
You see that?
Yeah.
Yeah.
So now it's spinning. So now the moment of inertia, or the bullet, is rotating about this hinge.
Mm-hmm.
So what's its moment of inertia about that hinge?
0.1.
It's mass times
The R squared.
0.5 squared.
0.5 squared. Oh, you said it right. Okay. Correct.
Okay.
And in the beginning, the door is not moving. It's only the bullet that's moving, so only the bullet has angular momentum to begin with. So the angular momentum in the beginning is the moment of inertia of the bullet times
Omega. So you have to divide by the radius.
that's not the way we want to do this. Sorry. What's another way that we can get angular momentum? Angular momentum is also equal to, we can get from just momentum. It's just R
Times the
cross momentum, right?
Mm-hmm.
So in our case, since the bullet's hitting perfectly perpendicular, it's going to be the magnitude of that times the magnitude of that times the sine of the angle between them. The sine of the angle between them is going to be 1.
How is it
radius.
1?
Yes.
Because it's going to hit perfectly perpendicular, so it's hitting at a 90-degree angle, so sine of 90 is 1. Okay, so the magnitude of our angular momentum then is going to be R, 0.5, times our momentum, which is the mass of the bullet, times the velocity of the bullet.
Yeah.
So that's our angular momentum, and that's our angular momentum throughout the whole system. Angular momentum is conserved, right?
Okay.
Because once the bullet hits the door, nothing else is acting on that system.
And there's no other forces, so it just keeps swinging forever, right?
So, potentially, yeah.
Okay.
I mean, maybe it eventually hits something over here, but we just want angular speed right after it hits. So right before it hits, here's our angular momentum. Okay. Now we know our angular momentum now when the door is swinging. Now when that door is swinging, we need to find an equation for the angular momentum of the door now.
Well, if it's conserved, then it's just...
So we got to go back to our equations for moment of inertia of the door. Because this is one of the ones we did. And I don't have that one memorized, and that's not one of the ones we wrote up there.
Moment of inertia of a door?
Of a shape like a door, of a rectangular shape like that.
Oh.
So this one is 1/3 n. So for the door, the moment of inertia of the door is equal to 1/3 the mass times this distance, 1 squared.
What's the mass?
Mass of the door. Sorry, I don't know why I plugged in one and not the other. We'll just keep Y there for a second. The mass of the door. Mass of the door.
Okay.
Right? So now, the moment of inertia when the bullet is inside the door, what's our total moment of inertia now? So our total moment of inertia, I, is going to be the moment of inertia of the door plus the moment of inertia of the bullet, right? That's going to be the moment of inertia when the bullet's impelled into the door.
So what's the moment of inertia of the bullet?
And the moment of inertia of the bullet, for some reason I erased that after we already found it, the moment of inertia of the bullet is equal to its mass times the distance squared.
Oh, that's right.
So it's just going to be the mass of the bullet times 0.5 squared, right?
Yeah.
And so another way that we have for calculating angular momentum is we know we can calculate angular momentum that way, or for its magnitude, we can use I times omega,
And okay, I see it.
right?
Yeah.
So we have, let me just write it completely as an equation. We have half the radius times the mass of the bullet times the velocity is equal to, parentheses, the moment of inertia of the door plus the moment of inertia of the bullet. Oops, what happened to that? Times the radius squared over 4, I guess. All times omega. So we're looking for omega, right?
Why is it over 4?
Sorry. R halves squared.
Yeah.
Good? The omega is what we're looking for, so we now have our equation for omega. Omega is equal to 1/2 R times the mass of the bullet times the velocity of the bullet, all over 1/3 the mass of the door times R squared plus the mass of the bullet times R squared over 4. Good?
Yeah.
And now we can just plug that in to solve this problem. So we have 0.5 times R is just 1, times the mass of the bullet, which is 0.01, times the velocity of the bullet, which is 400, all divided by, we have 1/3, 1/3 times the mass of the door, 15, times 1 squared, plus the mass of the bullet, 0.01, times 1/4.
The radius is 1,
Yeah, the radius of the door is 1.
but isn't it hitting in the middle?
Yeah, but you
That's why we did R halves, 1/2 R.
Oh, I see.
And it comes out to 0.3999, or 0.4 if we round. So this comes out to roughly, to two significant figures, it would be 0.40 radians per second. So there's our angular speed.
Is that fast or slow?
0.4 radians per second.
Well, 1 radian is half of
1
a second.
radian is almost 60 degrees. Right?
Oh, yeah.
So in 1 second, I mean, it's open like, I don't know, not much.
The bullet
It's
goes
not gonna
through.
fly open. A bullet can't hit very hard.
But
Right.
if it was at the end, it would be a lot more different, right?
It would increase it, yep.
But it wouldn't fly open still?
It still wouldn't fly open, no.
This isn't an Old West movie.
Yeah. Did you not watch our lecture talking about momentum? I realize you weren't here.
Oh.
I watched some.
Conservation of momentum when you, have you ever shot a gun before?
Yeah.
Okay. The momentum that the bullet has leaving the gun is exactly equal and opposite to the momentum of the gun recoiling on you.
Yeah, I remember you saying that.
Yeah. And how hard does a gun recoil on you?
Not very.
Not that hard. So the recoil hitting against a door that was on completely frictionless hinges, yeah, it would open the door, but it's not going to fly open. It's going to be a good hit to the door, right?
Yeah.
Yeah. So yeah, bullets don't have a lot of momentum, despite what every movie shows, where you shoot a guy and he suddenly goes flying back. Not real.
So really, if you shoot a guy, he's just...
You just
It's like hitting them with the recoil of the gun. That's how much momentum they experience. Now there's a lot of pressure, so it pierces into them, and does a lot of internal damage, but no, it's not going to knock you over to get shot. Okay, that finishes, since we're not going to do gyroscopes, that finishes the exercises for that. Huh?
How does that work with like arrows?
Arrows have a lot more mass
A lot more mass.
than a bullet.
But they don't have like any, not a lot of recoil, except string.
It's not the same thing. With a bullet inside of a gun, there's a little explosion that goes off.
Mm-hmm.
So internally, you aren't doing any work on the system to make that happen. It's an internal explosion completely contained within the system. A bow, you're doing work on the system the whole time. They're very different. Because pulling back on a bow, as you let go, the bow does work on the arrow for that period of time. It's like you deformed the bow. That's more like stretching a spring and then letting it go. It's not the same thing. You took energy, stored it as potential energy, and then converted that potential energy into kinetic energy. But you did work on the system.
Okay.
Yeah, that makes sense.
But how could you think about that momentum-wise? The reason it doesn't work is because the object is still being deformed as it's going forward. So, yeah, it's too hard. Momentum doesn't work well when thinking about a bow and arrow. Because there's deformation going on from the start. Should that matter? Because it's like you're slowly giving it its momentum. And you're resisting over a longer period of time. It's not one jolt.
Yeah.
So a much bigger time frame to absorb it. But yeah, when an arrow hits someone, that has a lot more momentum than a bullet. And so that'll knock you over. Well, I don't know if it'll knock you over. We can try and calculate that. Anyways, so next chapter now. Although we're kind of low on time, aren't we? The next chapter is a super easy chapter, one of the easiest chapters in the book. Okay, one of the easiest chapters in the book, and the basic notion to get from this chapter, well, there's two basic notions. The first basic notion is the idea of center of mass and center of gravity and how those are related. If you have a body that is pretty uniform in density, then center of mass and center of gravity are basically the same things. And so you can find the center of mass and the center of gravity of any weird object by kind of just figuring out how gravity pulls on them to find their center of mass or their gravity. So if I can balance a sink, however I balance it, if I can get balance, I can't get balance, but I get close to balance somewhere around there,
Okay.
then that means that its center of mass has to be somewhere around here, and that I have to be holding up its center of mass.
Mm-hmm.
And when we talk about center of gravity, when we say center of gravity, we mean the point that you can pretend gravity is pulling on that thing. Notice that when I set this whole thing up, gravity is pulling on it everywhere, from left to right, but I can treat all the mass as being concentrated at its center of mass or its center of gravity, wherever gravity is pulling on it. And so if I just hold up that one spot, that seems to be enough to counter out all the gravity pulling on this object everywhere. I can pretend like all the gravity is concentrated in that one single spot. And there's a lot of tricks for finding those spots. Get like an odd shape here. Here's an odd shape. Trying to find that thing's center of mass. Good luck, right? That's going to be a nightmare.
Yeah.
But if I were to balance this thing on my finger, and you can't really see where I'm holding it, but so if I balance it on my finger, I know that my finger is right here. And if I were to draw a line straight down through there, that line has to be going through its center of mass somewhere. And so if I hang it up in some other different way, and draw a line straight down from my finger, the center of mass also has to be lined up with my finger somewhere. And with those two intersecting lines, you can find the center of mass of any awkward shaped object.
Oh, I see.
This is kind of a bad example to see it with, but something like a book that's too simple to see it with. But so I hold the book like that, so its center of mass has to be lined up somewhere on this axis. And then I hold it like that, now its center of mass has to be lined up somewhere on this axis. Look at where those two lines intersect, and you found a point for your center of mass. In 3 dimensions, you actually need to take it from 3 places to find exactly its XYZ.
Yeah.
But so, an object always acts as though you can always treat an object as though all the gravity is just acting on its center of mass. You don't need to add the gravity acting in a bunch of different places. And we already talked about how to calculate the center of mass.
Mm-hmm.
Center of gravity, center of mass. So, not a big difference between center of gravity and center of mass. Center of gravity, the point you can act like gravity's pulling from. Center of mass, you already know is the center of mass.
Yeah.
Those are almost always the exact same point. So unless some problem gives you very specific information to the contrary, those are the same point. And we actually used the intuition for center of gravity to talk about center of mass to begin with. We talked about, when we first talked about center of mass, we talked about some sort of balancing beam. And what do we have to do to make things balanced? And whatever made it balanced we called the center of mass.
Yeah.
Wherever it turned out to be balanced, that was the same thing as finding the center of gravity for that system. So we actually use center of gravity to talk about center of mass, and now we're going to use center of mass to talk about center of gravity, a bit circular there.
Okay.
Just to give you intuition for the equations. Okay. So that one, center of mass, center of gravity, pretty much the same thing, nothing new there. Interesting thing that we're now going to talk about though is equilibrium, a system being at equilibrium. Up till now we said a system is at equilibrium when the net forces acting on the system are zero. Right?
Okay.
We're going to add a quick qualifier for that. It's almost, it still says the same thing. But, well, no, it doesn't say the same thing. A system now, we're going to say, is at equilibrium when the net forces and the net torque on the system are zero.
Net forces and net torque, okay?
Yes, that's when it's at equilibrium. And when it's at static equilibrium is when the net force and net torque is zero and the object's not moving. Static meaning not moving. And so we're going to do a lot of problems where we're going to do a lot of static equilibrium problems. Problem where the object's not moving and it's at equilibrium.
Okay.
Okay? So quick intuition really quick to tell me which of these objects are in equilibrium. So let's say that I have a force F pulling up right here, and I have a force F pulling up right here, and I have a force 2F pulling down right here. Is that in static equilibrium? Is that in equilibrium, we'll just say?
Yeah.
Yeah. Okay, what about if we take it and I have a force pulling up right here of F and I have the exact same force pulling down right here? Is that in equilibrium?
No.
No. Why not? Yeah, you're using your intuition there that that thing is going to start spinning, which is good. Notice that if we add up the net forces on this object, they're zero.
But the torque isn't.
But the torque is in the same direction on both of them. This is giving a positive torque. This is also giving a positive torque.
Yeah.
Remember how to trick if it's positive. Here's our position vector for each of those. There's a position vector for that. There's a position vector for that. You do the position vector cross the force vector. Position cross force gives me my torque is coming out, right?
Okay.
Once again, if I do position cross force, my torque is pointing out. So these are both giving a positive torque, if we want to call it the z-axis positive. So these are both giving a positive torque. Notice up here we had positive torque from this, negative torque from this, and then no torque from this.
Yeah.
Good? Okay, so we already remember how to calculate center of mass. Let's briefly talk a sec about something rolling, like a car falling over. When will a car or a truck tip over? So if I've got some slanted road, and I've got some car on the road, and then I've got some big truck on the road, how do I know when something's going to tip over? And when it's going to tip over is, you find its center of mass, draw that vector. If that vector is still supported, if it didn't get outside where this object is supported, the object won't tip over. If it gets outside, then it will. So if you get a higher center of mass, and now we draw this thing's gravity vector, and say that it barely comes outside that, now it's going to tip over.
Yeah, that makes sense.
So that's when an object tips over. It's when its center of gravity, when you draw the vector from the center of gravity, it gets outside the supports. And so you have the object tip over. So lower center of gravity things are harder to tip over, which makes pretty good intuitive sense, right?
Yeah.
So let's do some simple examples now. Walk the plank. A uniform plank of 6 meters has a mass of 6 meters and a mass of 90 kilograms, rests on a seahorse separated by 1.5 meters, and we want to hold up something. Yeah. So here's our plank. And our plank is 90 kilograms. Now we can treat this as though all the gravity pulls down right at the center of this thing, right?
Okay.
And we know that the length of this thing is 6 meters. With me? We have a seahorse holding this thing up. These are separated by 1.5 meters, right in the middle. You with me?
Yeah.
That you used to saw on.
Sawhorse.
Huh? Yes.
That called seahorse.
Sawhorse. I can't believe I said seahorse this whole time. That you used to saw, the sawhorse. Yes. Okay, sawhorse. Anyways, so, and the sawhorse is centered around the very center of this log. So what's the distance over here? You're going to do 6 minus 1.5 divided by 2.
Yeah.
6 minus 1.5 equals 4.5 divided by 2. It's going to be 2.25. So this is 2.25 meters.
The other side.
And then the other side is also 2.25 meters. Okay, so the question is, now Jack wants to come stand at the very end of this. How much can Jack weigh before he starts tipping this thing over?
Okay.
You with me?
Yeah.
So notice that if Jack starts tipping this thing over, then what's going to happen is this is no longer holding up the beam. And this ends up being the only one relevant. Right?
Yeah.
So when we get it perfectly balanced, when he barely starts to get this to lift, this part doesn't even matter. And it's just when the beam has enough weight on this side that it's canceling out his weight on this side, right?
Okay.
So we can treat the weight of the beam as though it's all completely centered right here, right at the center of mass. Right?
Okay.
So the board is going to create a torque right here. Jack's going to create a torque right here. Those torques are in opposite directions. As long as those torques are equal, Jack's good. Right?
What do you mean a torque?
Torque. Force
You're
times
saying there
radius.
needs to be one on the opposite end? Going the opposite way?
No,
We're trying to find out. Jack is trying to make the board rotate this way.
Yes.
The board is naturally wanting to rotate this way.
Yes.
That's the torque. Jack is producing a torque that way. The board is trying to produce a torque this way. It's trying to get to rotate that direction, right?
Okay.
So the torque of the board, in this case we have the torque of the board is perfectly equal to the torque of Jack. That's what we're looking for. The scenario where that's the case. That's the most Jack can weigh.
Yeah.
Okay. So the torque of the board now is just going to be its mass times its distance. What's the distance from here to here?
0.75.
0.75. So the torque of the board is 90 kilograms times 0.75. The torque of Jack is what? Whatever Jack's weight is.
Okay.
Oh, oops. This was just a mass, not the weight. We need the weight. It's a force.
So it's 90 times 9.8.
So it's 90G
Okay.
times 3/4. Right? That's the torque of the board. The torque of Jack, it's his force times his distance. Remember, how do we calculate torque? In general, it's force times R times the sine of the angle between them. Our angles are 90 degrees.
Yeah.
Okay, that's all I'm getting. Okay, so the torque from Jack is going to be his mass times his gravity times his distance. His distance is 2.25, or if we write that in terms of force, that's going to be 9 force.
Okay.
You with me?
Yeah.
Okay, cancel out g's on both sides and multiply both sides by 4. So we get 90 times 3 is equal to m times 9, right?
So it can be 30.
So m equal to 30 kilograms is the max Jack can weigh for this system to not topple, for it to stay in equilibrium.
That's not very heavy, is it? 30 kilograms?
I don't know. And 30 kilograms, same thing they got.
Okay.
Small.
Okay, next one. We've got some car, and it carries 53% of its weight at the front and 47% of its weight on the back. And I guess we're gonna have to find its center. But so we got some car here. Whatever. And its tires here, from where they touch the ground, are separated by 2.46 meters.
Okay.
And we also know that the front of the car, so here's the front of the car, the front tire holds 53% of the weight, and the back tire only holds 47% of the weight.
Okay.
Our job then is to find the center of mass.
Find the center of mass.
Yeah, find out where the center of mass is located in this direction. Right?
Okay.
Okay? So, similar type of thinking. You could imagine that the way that we solve this problem is we take the car, there's just this tire, that's all I care about, and I stick it on a board, and I need to find out where do I need to put this board to perfectly balance the car. And that will be its center of gravity, right?
Yeah.
Okay, so that's the idea that we're going to think about. So then each of these tires produce a torque, and we need their torques to be equal.
Okay.
Okay? So let's say that we say its center of mass is somewhere at x. And we'll imagine that this is our coordinate system counting this way. So let's pretend x is our center of mass and we're going to be looking for x. You with me?
Yeah.
So then the torque from the front tire, we need to equal the torque from the back tire, right? The torque from the front tire is going to be its weight, 0.53, times 0.53 W. We'll cancel out W's from both sides.
Okay.
But I guess I'll leave it for now. 0.53 times its weight times the distance it is from the center of mass. If I call the center of mass x, then this distance from the center of mass is just x.
Yeah.
Right? This is equal to the torque from the back tire. That's going to be 0.47 times its weight times its distance from the center of mass. This distance.
Which is also.
This distance is 2.46 minus x. X is the distance from here to here.
Oh, I see.
Because I'm saying my x-axis is going this way.
Yeah.
So here's 2.46. X is somewhere right there, right? So this distance is this distance minus this distance. So that's going to be 2.46 minus x. With me?
Yeah.
Okay. So we're going to solve for x. Really quick, I'm going to divide both sides by w and times both sides by 100.
Okay.
So we're going to get 53x is equal to 47 times 47 times 2.46 minus x. Right?
Yeah.
Or in other words, we get 53x is equal to 47 times 2.46 minus 47x. Right? Plus 47x to both sides, and we get 100x is equal to 47 times 2.46. Right? Or x is equal to 0.47 times 2.46, whatever that is. Or it's 47% of the distance over, which we probably could have already guessed. So 2.46 times 0.47, and that gives us 1.156 meters. So x is at roughly 1.156 meters. Now let's see what the problem was actually asking us to do. Find the distance between the, how far is the front rear axle, how far in front of the rear axle is a car's center of gravity? So we were actually looking for this distance.
So just
Which is that, right?
No, this is this distance. We found x, this distance. They want us to find this distance. So 2.46 minus x.
Oh, that is, yeah.
So they want 2.46 minus that number we calculated, and it comes out to 1.3 meters. Check their answer. Oh, must have been at the bottom. 1.3 meters. Okay, we did it right.
Okay.
Okay? There's a messier one. Okay, another one with a static equilibrium. Lots of forces coming into play here with the ladder. Okay, we've got a ladder leaning up against a wall. So, got the ladder leaning up against the wall at some angle theta. The ladder has some mass. Let's give it some thickness so we can label its mass. So, make the ladder kind of boxy. The ladder has some mass, we'll call that its mass little m. And there's going to be a person on top of the ladder who has a mass big M.
Okay.
We'll just read the problem real quick. Sir Lancelot, who weighs 800 newtons, is assaulting a castle by climbing a uniform ladder that is 5 meters long. So we know the length of the ladder. We know L. We know the two masses. 5 meters long. Oh. So Sir Lancelot is climbing the castle ladder, which is 5 meters long and weighs, the weight of the ladder is 180 newtons. The bottom of the ladder rests on a ledge and leans across the moat in equilibrium against a frictionless vertical castle wall. The ladder makes an angle of 53.1 degrees, but the horizontal Lancelot pauses 1/3 the way up the ladder. So we also know this distance, which what should we call that?
1/3 the length.
Yeah, but alright, we'll just leave that 1/3 length. Where he's located. Okay. Find the normal and friction forces on the base of the ladder. Find the minimum coefficient of static friction needed to prevent the ladder from slipping at the base. Find the magnitude and direction of the constant force on the base of the ladder. Okay, so here's what we're going on. I'm going to draw the picture again over here to draw just the forces. Theta. We don't need to label it. We'll just say that's our angle. So all the forces acting on the scene. First off, at the bottom of the ladder, we have a normal force pushing up. So I'll call that the normal force at the bottom. We also have static friction pushing this way to stop it from moving. Right?
Okay.
Force of static friction. We have the weight of the ladder, which we'll call, W of the ladder. We have the weight of Lancelot. Crap, those are both L. We'll just say of the man. So weight of the ladder. We have the weight of the man pulling down.
Yeah.
And then we have the normal force from the wall pushing this way against the ladder. And then it was told to us that the wall is perfectly frictionless, so there's no friction with the wall. These are all the forces involved.
Okay.
Getting a little messy, huh? Alright, so
Okay.
once again, but we know that the system's in static equilibrium. So the net force is in the x direction, 0. The net force is in the y direction, 0. The net torque, 0.
Oh, and that's simple.
Okay?
Yeah.
Alright, so the net force is in the x direction. Let's see what we have. We have the normal force off of the wall, which, let's set up our coordinate system like this. For a positive and negative. So friction is going to be positive, static friction is going to be positive, minus the normal force of the wall is going to equal 0, right?
Yeah.
In the y direction, the force is in the y direction. We're going to have
Weights.
the normal force at the bottom minus the weight of the man minus the weight of the wall, or of the ladder, is also equal to 0, right?
Okay.
Now torque. Where is this rotating about if it's not really rotating?
It would rotate around the center of mass, right?
You could do it from the center of mass, you could do it from the wall, you could do it from the bottom. It turns out that since it's in static equilibrium and it's not rotating, pick any axis of rotation you want, then that torque around that axis of rotation has to be 0. Because it's not rotating around any axis. So pick any axis you want. Pick the one that's most convenient for you.
Is the center of mass most convenient?
Typically no. But it could be.
Okay.
So typically you just want to pick the place where the most forces are, because then they give a torque of 0. So we're going to say it's rotating about this point.
Okay, I see.
Because then this produces a torque of 0 and this produces a torque of 0. And we just have to worry about the torque of that, that, and that.
Gotcha.
But we could have picked it anywhere. We could have picked it up here, we could have picked it there, we could have picked it there. Could have picked it anywhere. Because no matter what axis of rotation you pick, this thing is not rotating about that axis, right? Because it's not rotating. So pick any axis you want, you know its rotation around that axis is 0. So I'm going to pick this point down here.
Okay.
So I'll maybe put an L there to remind us of. That's our origin for rotation. So then our torque is also equal to 0. We're going to get a positive torque from the normal force and negative torques from these two things, right?
Would the normal
Yeah, that makes sense.
around give a normal speed?
No, because we picked this to be our axis of rotation. And so imagine that this thing actually can swing around this where it's hinged here. Pushing on the hinges doesn't rotate it. That's the amazing thing. That's the trick to solving a lot of these problems, is to pick a good axis of rotation. Make sense?
Yeah.
Okay, so the torque now, how do we calculate the torque? We have the torque from this thing. How are we going to calculate that?
Torque of which thing?
The torque, so now we have torque from 3 forces. This force, and this force.
Yeah.
This gives us a positive torque, this and this give us a negative torque.
So those two combined minus that.
Well, the torque-
Right, but we need to write out the torque. This isn't the torque. What's the torque from this thing? It's not just NW. How do I get its torque?
It's
We need to find the component tangential to that, right?
we do? I'm
Yes.
confused.
Or you could use the magnitude of it. Look, in general, what's torque? Think about this now as a vector, and think about the position vector from here to here as r.
Yeah.
Then the torque, in that special case, will be that position vector crossed with the NW vector.
So the torque would be just R, or the length of the ladder, right?
Sure.
Cross with all those forces.
Well, we have to represent that as a vector. I don't want to represent that as a vector. I'd rather just find the magnitude and use the fact that it's positive. So the magnitude of the torque then is equal to R times NW times the sine of the angle between them.
Is it so?
Just for that one though, and you have to do that for all three, right?
Have to do the same thing for that, have to do the same thing for that.
Okay.
You with me?
Yeah.
Okay, so we can do this however we want. Let's redraw our picture now. Our R in this case is shooting off like this, right? At an angle, we know the angle, theta, whatever it is. This is going this way. So what's the angle between them? Let's call this one phi for a second. What's this angle over here, theta? That's the angle between them.
Yeah.
You with me? So when we're calculating the torque here, the torque, our first torque is going to be the normal force of B times R, or in our case, the length of the ladder, L, right? Times the sine of the angle between them. The sine of our angle is going to be,
The normal force of
sorry,
B.
we didn't write theta up here anywhere, but we know what this theta is. That's given to us. So if this right here is theta, then this over here is 180 minus theta, right?
Yeah.
So times 180 minus theta.
Is that normal force sub B supposed to be normal force sub W?
Oh, yes, thank you.
Okay.
Good catch. Okay, so now let's think about it for our next ones. What about for this one and for this one? We gotta get their torque as well. So their position vector, once again, looks just like this, at some angle theta. They're pointing straight down. Right?
So it's theta plus 90 degrees?
So the angle between them is theta plus 90 degrees.
Okay.
So, and notice that that's going to give us, well, no, that's fine. That's its magnitude, but these torques are negative. Okay. So, times W of the ladder times
1/2 L?
1/2 L,
Okay.
I'll just say L over 2, times sine of theta
135.
plus 90.
Yeah, sorry.
And then we'll also, after that, we'll minus the weight of the man times the ladder over 3 times the sine of theta plus 90. Right?
Yeah.
Now, there's nothing wrong with that approach, and you can use that approach. I don't like trying to just make it make sense with the formula. I'd rather just reason about the picture here. So I like drawing right triangles. And I like saying, how much of this force is acting perpendicular if I move NW down here, end of the wall down here, and if we try and draw a right triangle here, this right here will be our theta.
Yeah.
And so this side then is going to be, the component perpendicular to it is going to be NW times cosine of theta. And NW cosine of theta and NW sine of 180 minus theta are going to give us the same quantity in this case.
Okay, that makes sense.
It's just the way I'd rather think about it than memorizing a formula. So I'd rather think about it as torque is equal to, in this case, we have NW times L times cosine of theta. Right?
Mm-hmm.
Similarly, if I extend this into a right triangle, here's where my theta is going to be. This was my weight of Lancelot was over here, and over here is once again going to be WL cosine theta. Right?
Yeah, I see it.
So minus the weight of Lancelot times L thirds cosine theta. Oh, that's weight of
Weight
ladder.
of ladder, yeah.
Weight of ladder times cosine theta.
And then the
I
same
wonder if I
thing.
did this one up here right. Let me think about this triangle one more time. Let's put the NW back right there. There's that. If I drop that down, here's my theta. Okay, yeah, I did that one wrong. It's going to be sine of theta. That's better. The component perpendicular is going to be sine.
Oh, gotcha.
I put my theta in the wrong spot over there. It's because the picture theta is too close to, that could be theta or that could be theta. My picture doesn't make a huge distinction there. So I wasn't thinking very critically. So that's NW. So this side, the component the component of it perpendicular to it is sine of theta.
So that means we did it wrong in the first one.
No, the first one we were just blindly following a formula.
No, it's-
Because sine of theta and 180 minus theta, those are actually the same thing.
you're supposed-
The height at 30 degrees and the height at 180 minus 30 are the same thing.
Yeah, that makes sense.
The height at 30.
And the height at 180 minus 30
Oh.
are the same thing. Okay, so minus, and then we have the weight of the man times L over 3, and then his is still going to be cosine theta. He's the same as weight of the ladder. And either of these approaches should be perfectly fine, doesn't matter which one you want to use, but we know that this adds up to is equal to 0, right?
Yeah.
That whole thing's equal to 0. Now, I can't remember everything that we were after, but let's just play with this expression a bit. So I know that NW times L times the sine of theta is equal to the weight of the ladder times L halves times cosine of theta plus the weight of the man times L thirds times cosine of theta. Right?
Okay.
Oh, I didn't do the same thing for these ones. So from this equation, I know that F of S is equal to NW, and from this equation, I know that the normal force at the bottom is equal to the weight of the man plus the weight of the ladder. So I know those two, and now I know this. Now that's extracting out the useful information. Right?
Okay.
Could you divide by L?
For this?
Mm-hmm.
Sure, that's a good idea. So we'll rewrite this one more way. we'll say the normal force of W times the sine of theta is equal to, now I'll put the 1/2 in front, 1/2 weight of the ladder plus 1/3 the weight of the man, all times cosine of theta. Right?
Yeah.
Anyways, let's now figure out what we were actually trying to do in this. So we know the weights. Let's write the numbers that we know. We know the lengths, we know theta, we know the weight of the man, and we know the weight of the ladder. Weight of the ladder. So let's see what we're trying to find now. Find A, the normal and friction force on the base of the ladder.
So the normal's easy.
So we're looking for NB is equal to, and we're looking for the friction force is equal to. So NB, we know what NB is.
Yeah.
It's the sum of those two weights, and it lists those weights. Lancelot's 800, the ladder's 180, so this is going to be 980 newtons. Just adding those two together.
Okay.
This is 800, this is 180. Okay, for friction, how are we going to get our friction? We have Fs equals the normal force from the wall.
So you just plug in for your weights, get normal force, and then you know your friction.
The normal force of the wall, we don't know the normal force of the wall.
But you can figure it out because you know all the weights.
We know the normal force of the wall from here. Okay, so here's how we get the normal force of the wall.
Yeah.
So we know that the normal force of the wall is equal to 1/2 the weight of the ladder plus 1/3 the weight of the man times cosine divided by sine is cotangent of theta, right? See what I did?
Cosine divided by sine, yep.
So let's plug that in. So we get 0.5 times the weight of the ladder was 180 plus 1/3 the weight of the man was 800.
That's a heavy man.
Wow, he's in full armor. It's supposed to be Lancelot. Times
Yeah, the ladder's back then.
the cosine of, what was our angle? You can write it up there.
Get into that.
Yeah.
Our angle was
Still. Jeff was
53.1 degrees.
This guy's 800. I don't know how much kilograms is in pounds.
No, it's 800.
He's 800.
And it's going to be roughly 268.
That makes more sense. That makes more
268
sense.
newtons,
Big boy.
which makes this roughly 268 newtons. Okay, see if we did that right. Oh no, that's for a different part.
Oh.
Where is it? Part A, that, is it hidden in all the writing? Torque, 268, okay, 268, that's what we got. Okay, part B. Part B is we were supposed to find the coefficient for static friction. So remember that for static friction, F of S is equal to the normal force times mu sub S. Right? Times some constant.
Okay,
That's how you calculate static friction.
now we remember, but yeah.
Okay, so F sub S in our situation, the normal force there, this is going to be NB times mu sub S.
MB or MW?
NB. The normal force where the static friction is occurring.
Oh, I see.
Right? So, mu sub S then is equal to F of S over NB, and I think we've already found both those, right? Yep. Yeah, we have, which is roughly, take that quotient, we take this, divided by 980, and we get 0.273. So roughly 0.273. They say 0.27. I guess we only have two significant figures. But why did they say 268 there? Being a little bit inconsistent. Oh well. Okay. Finally, we were supposed to find the net force acting at the bottom of the ladder. So there's two forces acting at the bottom of the ladder. There's a force of friction acting that way. There's a normal force acting that way. What's the net force at the bottom? That's what we're looking for.
Isn't it just those two forces together? Oh no.
Yeah, we've got to add those together. So the force at the bottom, let's find its magnitude. Its magnitude is going to be the square root of this one squared plus that one squared, right?
Okay.
What are you looking for?
The net force acting at the bottom. This force plus this force, we're looking for that force vector.
Okay.
So it's going to be a force, here's the magnitude of that force, and then we also need to get its direction. So theta at the bottom for that force is going to be the arctangent of, let's see which one's the y direction, and b over f sub s, which is actually mu sub s, so arctangent of mu sub s. Anyways, you plug those in, and there's no point in me plugging that into a calculator. You get what you get. So this one comes out to 1020 newtons, and this one comes out to 75 degrees. This is the direction the force is pointing. Because the normal force is a lot bigger than side friction. Okay,
Yeah.
so we solved that one. Next example looks like it's pretty similar, but using someone holding a dumbbell. So shouldn't be too much different. Stress, strain, tensile stress, tensile strain. So for the next section, the last section, 11.4, chapter 11 is a small chapter. So for 11.4, the last thing we're going to be talking about is stress and strain, or different things like this, and how basically applying forces to materials can stretch materials or compress materials. For example, steel stretches. I could take a piece of steel, and if I apply a force to it, steel stretches a little bit, right?
Just a little bit though. Right?
Just a little bit. It's a teeny tiny amount, but it does stretch. Or you can also compress steel a little bit. You might have noticed in sidewalks, every now and again, then they have like a little almost cardboard looking film thing in the sidewalk. And they do that every so often. Why do they put that there?
So when it stretches, then it won't break the sidewalk.
Because when it heats up, it stretches, and then when it cools down, it contracts. And so those are designed to expand and contract to fill those gaps, like your sidewalk doesn't. You'll notice people who do a crappy job pouring sidewalks, the sidewalk sticks out like that.
Mm-hmm.
That has to do with how it's expanded. So not quite the same exact concept, but similar. For any material, no matter what it is, if I push on this material, it is contracting some. A really small amount, but it is contracting some. And if I pull on it, it is expanding some. Right?
Okay.
So, that's what we're going to be talking about a little bit, is the stress and strain that you put on an object, how much force you put on an object, how the force you put on an object is related to how much it compresses or how much it stretches. And then similarly with putting pressure on an object from a fluid. So I could take a metal bar and I could pull it, or I could push on it to compress it and stretch it a little bit, or I could take you, and I could take you and stick you 30 meters underwater. There's a lot of pressure there. Your volume shrinks.
Okay.
Or I take you and I stick you in outer space. Your volume expands some.
Yeah, that makes sense.
So having a pressure all around an object shrinks its volume, or making the pressure smaller increases its volume. Similarly, when we're just talking about a still, just in a linear direction, pushing can shorten the length, and pulling can expand the length. And we want to see how these are related.
Doesn't that
For different
correlate
materials.
with the material?
Yes. So you're going to have a table of constants that you look up on a table for different materials, for like aluminum, brass, copper, crown glass, iron, lead, nickel, steel, etc.
Crown glass.
I have no clue what crown glass is. I'm not saying my syllables right. Okay. So we have a relationship between stress and strain. And that's going to be a constant for some material as long as you're not, as long as the numbers aren't too big here that you're talking about.
Is that a Y?
Yeah, so the first one that we're going to talk about is Young's modulus. So it's a constant which we use a Y for the first one.
What?
Young's modulus is what that constant is called. And it's based on different materials.
Or what?
Sorry, we're not into that one yet. This, we're starting out with Hooke's law, which is going to be some constant. We've done a special case of Hooke's law with springs. But here's what it is in general. As long as you're not applying forces too big or forces too big, then stress and strain are related by some constant.
Okay.
The amount that the system is stressed is related to basically how much it's stretching or compressing is related to how much force is being applied to it.
Yeah, that makes sense.
And they're directly proportional as long as you're not getting crazy with it.
Okay.
When do you start getting crazy with it? When you start deforming the materials. A slinky follows this rule until I stretch out the slinky. Uh-oh, now it's not following the rule anymore. I've deformed the material. Still, when I pull on steel, it follows this until I pull the steel too hard. Then it doesn't follow the rules anymore.
Okay, that makes sense.
So within a margin of error, this is the case. So the first one that we're going to talk about is a special case of this, which we call tensile stress and tensile strain. So that's the first example of this. But the big picture, stress and strain are equal to some constant. So we'll put that up to the left over here, and we'll look at three special cases. So stress over strain are constant. So the first one that we're going to look at is the constant we're going to look at, they call it tensile. Tensile stress, this is when we're looking in the linear direction. So this is just pulling on a piece of rebar, something like that, trying to stretch out steel.
Okay.
Tensile strain is going to be a constant, which we're going to use Y for this one. It's called Young's modulus. And tensile stress and tensile strain, how do we calculate these things? Well, tensile stress, this is the force that's being applied to it. And you already have intuition for what I'm about to write. Maybe I'll write them to the sides over here. Well, we can write up here. Tensile stress, maybe I'll just write it. It's the force perpendicular to the area divided by the area. And let's make sense out of that one really quick. If the cross-sectional area of the steel beam I'm pushing on, so if I have a really thick piece of steel and I try to compress that, for the same amount of force, it's not going to compress as much because of how thick it is.
Mm-hmm.
Versus if the steel were really, really thin, then my pushing on it can compress it a lot more.
Yeah.
So it's related to the cross-sectional area. The bigger the cross-sectional area, the more force I have to apply to get the same amount of stress.
Mm-hmm.
Yeah, that makes sense.
That makes sense? And the force only matters if it's perpendicular to the area. If I'm trying to compress this whiteboard into the wall, and I push my force this way, oh, that doesn't compress it. I have to push directly into it. So it's the component of it perpendicular to the area. Pushing down on the area, that's what that means.
Yeah.
Good intuition there?
Mm-hmm.
Okay. So the stress, the amount of stress you produce in the material has to do with, it's directly proportional to how big of a force you apply, and it's indirectly proportional to how much area you're pushing on. More area means you're producing less stress with the same force.
Yeah.
More force means you're producing more stress with the same area. So bigger force increases the stress, and less area increases the stress. Am I overstressing that? You got it?
Yeah.
So tensile stress, there's the equation. Now, tensile strain, this is how the material changes. It's the change in length you get in the material. I think they use a lowercase l. We'll use a lowercase l. It's the change in length you get in the material per length of the material.
Change in length per length?
Yeah, so imagine this for a second. Imagine I've got some material, and I apply some force so that it compresses 1 inch. Okay? Well, if I double the length of that material, and I apply the same force, how much is it getting compressed now?
Double it.
2 inches, right?
Yeah.
So, it's the change of length that you get divided by the initial length, I guess, is a better way to say it.
Okay.
Okay?
Yeah.
The stress it produces in the material and how it changes the material, the strain it puts on it, how much it stretches it out or compresses it.
Okay.
That's the first one. The second one is when we're talking about pressure in a fluid. Now, it just helps to note that pressure in a fluid, how do we calculate pressure in a fluid? Sorry, not rho, it's a P. Pressure in a fluid. We talk about the amount of force being applied per area. The amount of force being applied per area. It's the difference between a bullet from a gun and the recoil from a gun.
Okay.
Why does a bullet do a lot of damage to you, but the recoil from a gun doesn't? If it's going to be basically the same force acting on you.
Well, I could assume
Because of the area.
Yeah.
It's the same force, drastically different area. A bullet is designed with just that. Maybe not think about a bullet versus a gun. Let's say I push a needle into you, and I only push with 10 newtons. And then I push a calculator into you, and I only push with 10 newtons. One of those has a lot more pressure than the other.
Yeah, that makes sense.
Because the area went down. So pressure is inversely related to area and directly proportional to the force.
Okay. So pressure is just a lot like stress? I mean, it is.
Stress is like the pressure, the tensile stress is like the pressure inside the material somehow.
That makes sense. Okay.
Okay, but no, this is like pressure, like even when we're calculating atmospheric pressure, this is like pressure when we're calculating pressure inside your car's tires. We'll do a lot more with pressure when we get to talking about gases in general.
Okay.
But just regular pressure, there it is, in a fluid. Okay, so now the next one we have is bulk pressure. This is when we're talking about in 3 dimensions now. Notice that that was across 1 dimension. And so we have bulk stress. Bulk stress over bulk strain. Bulk somehow trying to make you think now it's 3-dimensional, not just 1-dimensional.
Gotcha.
And this one is equal to negative the change in pressure over the change in volume over the initial volume. And we can make sense of this one again.
Change in volume over the original volume?
Uh-huh.
So why negative?
Yeah, let's take it one piece at a time. Let's start with the delta change in pressure here.
Okay.
So up here we just had a force over an area. Here we had a change in force over area. So when something's in a fluid, you always have a pressure acting on you.
Yes.
When I change the pressure, that's going to change your volume. If I suddenly increase the pressure, your volume's going to get smaller.
Yeah.
If I decrease the pressure, your volume's going to get bigger. That's where the negative sign comes in. If delta P is positive, I make the pressure go up, your volume goes down.
Oh, so B stands for volume?
B over here is just a constant.
Oh, okay.
V stands for volume. Notice we can put the delta V over on this side. Let me rewrite this one more time. So the change in pressure is equal to some constant B, who cares? That just depends on the material, times negative the change in volume over V naught. This is reworking this equation, just putting this over here with the negative.
Okay.
That's why the negative's there. You see it?
Yeah.
If the pressure goes up, the volume, the change in volume has to be a negative change. If the pressure goes down, so if this then becomes negative, this has to also, the negatives will cancel out. That means your volume is now increasing. So that's why there's a negative sign in there.
Okay.
That makes sense.
Good?
Yeah.
Yeah.
So that's bulk stress and bulk strain. And then the last one of these has to do with shear stress and shear strain. How can I give you shear stress and shear strain? All right, I'll just have to try and draw that picture here. So we've got some cube. Maybe I'll just show you the picture and then talk about the picture, give you an idea for shear. Because it's like warping it, pushing it to the sideways, making it stretch to the side. So, give you the picture here, try and hold this on the book here so that the camera can see it. So we have some cube right here.
Mm-hmm.
And what we're going to do is on top of the cube, we're going to apply a force to the left. And at the bottom of the cube, we apply a force to the right. You with me?
Yeah.
And so it's going to warp it. The top's going to move over to the right, the bottom's going to move over to the left some. And there's going to be this total displacement now between the top and the bottom, some distance x. Some distance x.
Okay.
So now that you've seen the cube, let me do just a two-dimensional version of it. So the cube before, it looks like this. This is some height, h, and it has some cross-sectional area, a, up here, right?
Yeah.
We apply a force on the top and the bottom, and that causes it to stretch and look more like this, right?
Mm-hmm.
So we get some displacement here, x, over some height, h, from applying a force, the force F here, and these two forces are parallel, and the force parallel down here, in opposite directions.
So the
And it
forces
creates a
have
shear.
to be parallel, right?
Yeah. One's pushing on the top, one's pushing on the bottom to create this shear. So that's what we're talking about. The force that will produce a certain shear in a certain material.
Okay.
Right? Some materials it's easier to get warp to work like that, other materials it's harder. Okay, so our constant for this one is S. And we call it shear stress, I think. Yes, and shear strain. And shear strain. And for this one, it's the force that you apply parallel to the surface area
So wouldn't that be 2Fs?
over area. No. It's the same area, it's the same force in both spots.
Okay.
So it's however strong that, I mean, I can see why you want to put a 2 here, but then I could just divide both sides by 2 and it just changes my constant.
Oh,
So the 2 is just accounted for in the constant. Okay, so it's the force you put on the area divided by the amount of x you can get, displacement you can get per unit height.
X over height?
X over height, where x is how much you got it to shear. You with me?
Yeah.
So let's make intuitive sense of this. First off, it makes perfect sense that the harder you push, the more you can get this to shear, right? And the more area it has, the harder it is to get it to do that, right? It's harder to do it with a thick material than a thin material.
Yeah.
So that's the cross-sectional area. Now the x here, per unit height, remember, if I apply 2 forces to something that's 1 foot long, and I can get to shear 1 inch, then if I apply those same forces to something that's 2 feet long, I'll get to shear 2 inches.
Okay.
So it's the amount you can get it to shear per unit height.
That makes sense.
Make sense? Okay, these are the 3 equations that you'll use over and over again. And there's a table for all these quantities for different materials. So there's a table on page 353, and it has a bunch of materials, and it lists you out what the Y is, what the B is, and what the S is for each of those.
Yeah.
So let's do an example now with one of them.
Okay.
Is this the first example? Yes. Okay, a steel rod 2 meters long has a cross-sectional area of 0.3 centimeters squared. So I know I'm dealing with a rod, its length is 2 meters, and its cross-sectional area is 0.3 centimeters squared. So we'll need to convert that to meters squared, probably. It is hung by one end from a support and a 550 kilogram weight at the other end. Determine the stress on the rod and the resulting strain and elongation. So here's the actual picture. This metal rod is hanging from the ceiling, and down we put some massive weight on here of 550 kilograms, which is going to produce a stress and strain in this thing. This thing is 2 meters long, and its cross-sectional area is 0.3 centimeters. Or in other words is, how do we even want to write that? I mean, this is the same thing as 3 times 10 to the negative 1 centimeters squared, which is going to be the same thing as 3 times 10 to the negative 5 meters squared. Probably the easiest way to see it. Right?
Okay.
Divided by 100 twice to get to meters.
Yeah.
Okay. Let's see. We got that. We got the area. We got that. Now we just need steel. Okay, this is a steel rod. Steel rod. And we're stretching it and compressing it. So this isn't the bolt, this isn't the shearing, this is going to be this one.
Yeah, because you're only going up and down.
Right, so I need to go look up what my y is inside my table and see what that constant is.
Okay.
And we go look up the y in the table. Hopefully they have it listed here. 20 times 10 to the 10, is that right? Let's just look it up in the table. We can't do that far back. Still, 20 times 10 to the 10. Okay, so this is 20 times 10 to the 10. And it's really hard to compress steel. Okay, so now what do I know? I know that this y for steel is equal to the force per area, the force divided by the cross-sectional area. What's the force? It's mg. So mg divided by the cross-sectional area over my initial length divided by my tangent length. Delta L divided by my initial length.
So
and
you're
we're looking for the delta L.
Okay.
Right? So move this to the other side. So we get delta L over L naught times y is equal to mg over a. So delta L is equal to mg times L naught over y times a.
Okay.
Right? And we come and we plug all these numbers in our calculator. We have the mass is 550 times 9.8 times 2 meters, right?
Mhm.
2 divided by 20 times 10 to the 10 times 3 times 10 to the negative 5. And we get 0.0017 meters.
Hardly moved at all.
So delta L is equal to 0.001, let's see, 2 decimal places, 18 meters. Or in other words, delta L is equal to 1.8 millimeters. 1.8 millimeters, okay. So that's how much that cable stretches out when we put 550 kilograms hanging from it.
That's pretty bad, eh?
Isn't much at all. So you'll notice that these problems aren't really that hard to solve. They'll just give you the constant, you plug it in.
Yeah.
So all 3 of them are basically doing the exact same thing.
So you're just trying to recognize which one's going with
Which one to use? Yeah, so I think that's the whole hard part with these problems is this is when it's all in 1 dimensions.
Mm-hmm.
This is when it's 3 dimensions.
Okay.
And then this is when it's shearing. I don't know how to give you good intuition for this one. Because this one's kind of 1-dimensional as well, but it's not stretching or compressing. It's kind of.
But that would be pretty obvious to us.
Yeah, I think you'd be able to figure out pretty easily. So it's a pretty easy section, I think, one of the easier ones. And we'll do a lot more with pressures down the road.
Okay.
So that's the end of that chapter, and then I think that's the last one before the test, and so
Test on Tuesday?
tests coming up, and you guys are free to go.
Okay, thank you.
Wow. Yeah.
Are we doing any chapters next week or just the tests?